Yeah, very happy to have Asher today to give us the talk on mini charge particles.
Thanks. Happy to talk to you all. So this is based on originally a paper from a couple of years ago, but predominantly on something that is in progress with people here. Well, Zach Bogorad is a postdoc here, as well as with Peter Graham and Hari Vermani. And the basic idea is how to use very old experimental setups. So originally dating back to tests of Coulomb's law by Henry Cavendish in the late 1700s, as you can see here in the middle, and how these things can be powerful tests, either reinterpreted or repurposed to look for Millicharged particles, new particles with some small effective electromagnetic charge. So part of the motivation for this, or part of the context that I'll be discussing, is particles that arise as a small component of the dark matter density. So this is, I mean, the main motivation is looking for particles that either can arise from cosmology or maybe produce locally. But one thing that one way that they can arise cosmologically is if they can make up a small subcomponent of the dark matter parameterized by some fractional parameter f sub dm. So this is just a fraction of dark matter in some new particle. And you might ask why a subcomponent. Usually we think about particles making up an order one fraction of the dark matter density. Why are subcomponents interesting? And one perspective you can take is just to note that something that makes up an order one density of the dark matter is special and kind of mysterious or unexplained in the sense that it has a cosmological density comparable to the baryonic energy density, which is famously exponentially sensitive to parameters in the UV from dimensional transmutation. So that's a mystery in itself. In that sense, something that has a density much different than the baryonic energy density is more generic. And there are various cosmological scenarios that give rise to very small cosmological densities of particles. So the simplest is just that of a thermal relic, something that freezes out from the standard model. For instance, things that have order one couplings in small masses are naturally a very small component. So for instance, something with an order one coupling and a mass comparable to the mass of the proton freezes out to be 1 part in 10 to the 10 of the dark matter density. Okay, just from the fact that it's able to overly deplete as the universe expands. Furthermore, this fractional value can be much lower, for instance, exponentially smaller, if the reheat temperature of the universe was never greater than the mass of these particles. In that sense, you can be exponentially small. Okay, so it's not so crazy or hard to get very small cosmological number densities of particles. And I'll talk about this a little bit more as I focus on a specific model, but there also can be local modifications to this. So if things make up a fractional density of dark matter in the galaxy, their density locally might be enhanced or suppressed depending on how they interact with the environment. And I'll mention some more specifics later on. But another reason to be interested in cosmological subcomponents, for instance, is the fact that there are huge gaps in coverage. So we're used to saying that, as an example, we haven't seen new physics either because it's very heavy or very weakly coupled. The class of models I'll be discussing about today are neither, but still there's a gap in coverage. And furthermore, most of the things that we know about dark matter, that's cold, collisionless, weakly coupled to the standard model, only applies to things that make up the entirety of the dark matter. Things that make up a sub% are essentially unconstrained. So as an example, sub% of the dark matter could have extremely strong interactions with normal matter. In fact, these small abundances and large interaction strengths go hand in hand from the point of view of thermal freezeout. And you might think, okay, if there's some percent of dark matter that's extremely strongly coupled to normal matter, why haven't we seen these things from the point of view of direct detection experiments on Earth? This is because these experiments are only sensitive to sufficiently weakly coupled particles. Particles that are extremely strongly coupled would cool down to room temperature or ambient temperature in the atmosphere and essentially shed all of their kinetic energy, or most of it, before getting to these detectors. So specifically, the fact that room temperature corresponds to roughly a few tens of millieV, and that's well below the typical threshold of direct detection experiments, implies that often these experiments are just not sensitive to very strongly coupled dark matter subcomponents.
All right, Asher, can I ask you a question about this? Can I stop you
Sure.
here? So Thanks. I mean, this is interesting. So I just like to check in about the second point, the strong
Yeah.
interactions, right? So if I and I'm specifically thinking about like bullet cluster type constraints. So roughly, you can for 100% dark matter, you can understand those constraints by just saying that the mean free path is less than the size of the cluster, right?
Right.
But now, if you really have a subcomponent that's say 1% and is very strongly interacting, it will have many, many mean free paths in general, right? And so are you saying that it doesn't matter if it's 1%, then you wouldn't see it at all in the bullet cluster, no matter how many interaction lengths it had, it would just be a tiny correction to what you think is the matter density or something.
That's
Is that
that's
right?
that's exactly right. You're essentially, and from that point of view, you're essentially hiding in the uncertainty in how many baryons there are in the galaxy
Yeah.
cluster. And also strong constraints arise from dark matter inheriting a pressure from coupling to the photon baryon fluid in the early universe. So now the dark matter has a pressure that reduces
Okay.
structure. That acts just like baryons in the early universe. So essentially, the uncertainty in how many baryons and how much helium there is, things like that, allows
Right.
you to hide this amount of dark matter in those components. Yeah, that's right.
Okay. Okay. Thank you.
No problem. Okay, so anyway, there's various possibilities for what these particles could be, but one particular example, which is in the sense that it's a simple model, is relatively unconstrained and potentially has detectable signatures, is the one that I'll be focusing on, is this case of particles with a small charge, so-called millicharged particles. So just given another motivation for this, I'll be focusing on how to detect very small densities of these particles. There's an irreducible density of these particles that can arise from just cosmic rays. So I'll be coming back to this towards the end. So the dynamics are a little bit more complicated. But everything that I'm going to be saying for the majority of the talk can be ported over to this. But cosmic rays are hitting the top of the atmosphere, creating showers of pions and vector mesons. If these millily charged particles are light enough, the particles in these air showers can decay into these particles, and there's an irreducible density of these particles just arising from these decays. And some of the techniques that I'll be discussing are actually sensitive to this irreducible density. So that's just another example. Okay, so that's the quick introduction for what I'll be telling you. The rest of what I'll be telling you is outlined here. So I'm going to be quickly taking you through kind of a tour of the parameter space of millily charged particles, where they're strongly coupled to normal matter, how they behave on Earth. So in fact, I'll show you how they can give rise to an overdensity of these particles on Earth compared to their galactic density. And finally, I'll be discussing how you can detect this terrestrial population using very old technology pictured here, if you can see my mouse. Originally, so referring to like these original experimental ideas by Henry Cavendish in the late 18th century. Okay, so let's just get started. What are these particles? What does this parameter space look like? And just to give you an additional motivation for this, I'm sure I don't need to sell you on this idea, but just to give the pitch, you can look at the standard model, note that particles couple to themselves and each other through long-range forces. It wouldn't be so crazy if some subcomponent of the dark matter sector was charged under its own dark U1. And you could ask, how could this thing couple back into the standard model? If it couples directly to things like electrons, protons, or neutrons, the number of these particles in some sense, this is highly constrained. Okay, so you can look for these new long-range forces being sourced by the Earth and acting on test masses in the lab. Those tests are so good that they typically constrain these standard model parts of these interactions to be subgravitational at the dimensionless level. If these are very, very long-range interactions at the level of 10 to the minus 24 or sometimes smaller. But a natural exception to this is if this long-range force couples to charge. Okay, the Earth isn't electrically charged. The bulk masses that people are using as detectors aren't charged. The universe discharges electric sources. So this possibility is relatively unconstrained and could arise, for instance, if this new A prime or new U1 had a small mixing with our photons, such that at low energies, these particles look like they have effective charge controlled by the product of this mixing and dark charge. This is a relatively unconstrained possibility. Now, more technically, I'm sure many of you know this already. This can arise from kinetic mixing, where the field strength tensors of these two U1s has some mixing controlled by epsilon, and a simple shift for instance, this dark U1 gives rise to this interaction structure where the dark charges, so the dark charge, a dark current, dominantly couples to the dark U1, but has a small coupling under RU1 parameterized by the small mixing parameter, such that these particles have a so-called millicharge or small charge that is small because of the small mixing parameter. Okay, but it's controlled by the product of this dark gauge coupling and mixing. I'm going to be taking this as a free parameter, but always in the back of my head, thinking of this as arising from some small kinetic mixing. And I won't be talking about insanely small kinetic mixings, kinetic mixings that might be at the level of 1 loop or 2 loop radiative mixings. So this is a kind of a bird's eye view of the parameter space that I'll be focusing on, spanned by the charge and the mass. Gray regions are excluded in gray here. These are excluded from accelerator searches, which kind of peter out at masses much greater than tens of GeV, considerations of supernova 1987A. And most of this parameter space is white, the way I've shown it. There are two main interesting regions of parameter space that I want to focus on. One is this red line. Okay, so above this red line, direct detection experiments are typically not sensitive. And this is because if you're living up here, these particles are rapidly shedding their kinetic energy before they hit the surface or before reaching a kilometer underground. And they just don't have enough kinetic energy to be seen above threshold in these experiments. Below this red line, direct detection experiments can be sensitive to these, or are sometimes sensitive to these models, but only if there's enough flux. So in fact, even below this red line, if these particles make up smaller than 1 part in 10 to the 8 of the dark matter, these direct detection experiments are typically just insensitive to the entirety of this parameter space. Now, another more conservative thing to ask is, where do these particles not necessarily slow down in the atmosphere, but where do they slow down on Earth? Okay, so this is a much weaker requirement. And it turns out that for charges above this blue line, these particles are stopping somewhere on Earth. Okay, they're able to exchange all their energy in a meaningful way and stop somewhere on Earth before doing something else, which I'll soon describe. So just to summarize, this red region is the region where direct detection experiments could potentially be sensitive to these particles if they make up a substantially large part of the dark matter density. Above this blue region, these particles stop somewhere on Earth. They shed all their kinetic energy, most of their kinetic energy on Earth, and their phase space is significantly modified. So these are not insanely large couplings, but it's enhanced by the exchange of a light mediator. So for charges as small as 10 to the minus 7, these particles can stop somewhere on Earth if they are the dark matter, or if there's some component of the dark matter. And you can ask, what happens to this population? Okay, so what happens to this population in this blue region of parameter space? That's essentially the next part of this talk.
Sorry,
Yeah.
can I just ask a real quick question? I'm sorry,
Yeah.
because I heard you say something about light mediator, but in this chart, you're only assuming just the Millicharged interaction and nothing else?
That's
Or
right.
you're gonna, that, what, I don't know what the light mediator was
Oh, sorry.
about, but,
The light mediator is the photon.
oh, okay. I've heard
Yeah.
of that particle. Thanks.
Yeah. I should have been more specific, but just through charge interactions, like through scattering off of a nucleus, just through the charge, that's where these particles are able to stop. Okay, so what happens to this population of particles after they significantly scatter off atoms and nuclei in Earth's environments? And the basic story is that there's a buildup in density. So I'm going to refer to the galactic population as a virial population, the virialized galactic population. And you have an incoming dark matter wind, just from the fact that the Earth and the solar system are moving throughout the galaxy, speed of roughly 10 to the minus 3. And once these particles scatter, there will be some small bulk outgoing velocity. And this could be for various reasons. Maybe they're heavy enough to become gravitationally bound. Or maybe it's just because they've cooled down, and so it takes them some time to random walk throughout the Earth, and so the effective outgoing bulk velocity is small. But just from conservation of flux, if this outgoing bulk velocity is small and the incoming bulk velocity, the dark matter wind, is much larger, you'll get a buildup in density just from conservation of flux. And there are two dominant contributors or populations that lead to this large terrestrial density. One is the accumulating population. So this is the population that's been, let's say, gravitationally bound and accumulating for 5 billion years or so, the age of the solar system. But there's also another population I'll refer to as the traffic jam population, which is not the population that has not yet reached hydrostatic or mechanical equilibrium on Earth. It's the population maybe that's just recently hit the top of the atmosphere and is finding where it wants to settle into. But because it has to slowly diffuse as it's approaching hydrostatic equilibrium, because it has to slowly diffuse, that slow movement implies a buildup in density, very analogous to just a traffic jam. Slow bulk velocity implies an enhancement of number density. So I'll refer to these two populations as distinct, but they're both kind of co-mixing with each other. They're both happening at once. Okay, so let me just first describe this accumulating density, which is the statement that if these particles are much heavier than the mass of a proton, their thermal velocity at room temperature is typically much smaller than the escape velocity of the Earth. So these particles can accumulate over the age of the Earth up to some efficiency. So the first thing you would do when thinking about this is, let me assume that these particles make up some fraction f of the dark matter. You could count how many particles have ever passed through the Earth, assume that they all get captured, let's say gravitationally. What's the volume average density? That turns out to be roughly 10 to the 15 per cubic centimeter, which seems quite large, but is, still like 8 orders of magnitude less than the normal terrestrial density. So it's very small compared to the density of normal matter on Earth, but very large compared to normal dark matter densities that we think about. But this really isn't the right thing to think about, because from the point of view of detection, if you're curious about directly detecting this population, you're curious about the density near the surface. And I haven't told you about where these particles sit. This is a volume average. So to answer where they sit, you can just write down essentially the hydrostatic limit of the Euler equation of fluid dynamics. This is what people sometimes call the Jeans equation if they're thinking about more astrophysical applications. But something that's in mechanical equilibrium will eventually settle into this attractor solution or steady state solution where the gravitational pull from gravity, Earth's gravitational field, will balance a pressure gradient. And for a uniform temperature ideal gas, that pressure gradient is just dictated by a temperature, which is the temperature of Earth, and a gradient in number density. So you can solve this. And what I'm showing you here is some arbitrarily normalized. So the vertical axis doesn't have any units, but the arbitrarily normalized radial profile of these particles on Earth. So Earth's surface is over here at roughly 6,400 kilometers. And what you find is this population is only relevant for a very small range of masses near the surface. This is because they have to be much heavier than a GeV to become captured. But once you go much, much heavier than a GeV, they tend to sink and tend to reside towards the center of the Earth, exponentially suppressing the density near the surface. Okay, so this accumulating population is typically relevant only for a narrow range of masses, around a few to 10 GeV. So the more interesting question is to ask, well, what about the other particles that haven't yet reached mechanical equilibrium? Maybe they're going to sink and dominantly reside towards the center of the Earth, but in the process of sinking, that slow movement can give rise to a large density.
Sorry, before you leave that,
Yeah.
the accumulated population. So the fact that the Earth is hotter in the middle doesn't somehow help by expelling stuff from the middle, or is that
It
an
does.
unimportant
It
effect?
does. It does actually puff them out substantially, but it's not enough. Right, the temperature near the core is like something like around 5,000 Kelvin, something around there. So it's like roughly an order of magnitude or a factor of 20 greater than near the surface, and it does puff them out away from the core substantially, but not enough. If that temperature extended all much closer to the surface, it would matter. But because the hot ball near the center of the Earth is so far away from us, it tends to not puff them out enough. So this profile that I'm showing you takes all the gradient of the temperature into account. Okay, so like I was saying, therefore this just recently arrived population is more relevant near the surface. The population that is just passing through us might be wanting to sit towards the center of the Earth, but still has to pass through the lab. And in the process of slowly drifting throughout the lab, there can be a large number density, not as big as the total accumulated number density, but still quite substantial and could dominate near Earth's surface. So to solve that, because this is a highly collisional system, you can just consider the first few moments of the Boltzmann equation. It becomes kind of a closed system for highly collisional particles. So you could just consider the 0th moment in the first moment, which is the continuity equation in the Euler equation. So n chi here is the number density of these particles on Earth. V sub chi is the bulk velocity, not the individual particle velocity, but the bulk motion of a fluid element. So this first line is just conservation of particle number. The second equation is F equals ma for a fluid, where there's a drag term coming from the fact that this dark matter fluid is colliding with air molecules, and that relative velocity sets up a drag. So this collision term becomes bigger for larger charges or larger cross sections. And the right-hand side is just essentially the effective force acting on this fluid, which comes from gravity. Whatever electric field happens to be present, there's an electric field in the atmosphere. There might be an electric field in the lab, so that will enter as well. And also, there's a push away from high pressure gradients. So these fluid elements will move away from regions of high pressure. So imagine we have some particles with velocity 10 to the minus 3 with number density in virial, the virialized galactic number density, and they're going to scatter and then get some number density in chi on Earth. So how do we calculate that? In the highly collisional limit, these two equations can be kind of combined into one algebraically into what looks like the diffusion equation. So this looks like continuity, but this J sub chi, the number current here, has two pieces. So it has one thing that I'm going to refer to as a drift velocity. This is a terminal velocity as these particles drift in an external field, and also just diffusion. So even in the absence of an external field, these particles are diffusing around, and they're diffusing away from density over densities of these particles, dictated by the diffusion coefficient d. So let me take you through these two terms. The drift velocity is some compensation. It's the pull of an external field plus compensated by the friction of collisions. So you see it's bigger if the electric field is bigger, the gravitational field is bigger, but smaller if the collision rate is bigger. So this is just the terminal velocity of these particles balanced by collisions and pull. And this diffusion coefficient parametrically is just the collisional mean free path times the thermal velocity. Okay, it becomes smaller as these particles become more tightly coupled. But this equation here is very simple to solve. It's equivalent to a random walk, but biased to happen in a direction of some external field. And you can solve this thing in very interesting limits, or in very particular limits. So let's consider first the small mass limit, where these particles are so light, they just don't care about Earth's gravitational field. They're going to come in, scatter, wander around, and then eventually leave, just evaporating off the Earth. So the important point here is because these things are interacting through the photon, the interactions are peaked at very small momentum transfer. There's some screening effects due to interactions with the atom itself and to see the charge. But typically these interactions are peaked at small momentum transfer, which implies that, let's say they punch in a distance L virial when they're moving with essentially a virial speed of the galaxy, and then they cool down. After they cool down, they'll take much smaller steps, what I'm calling L thermal, because they've cooled down the room temperature and the interaction rate becomes enhanced. And that's an important point. So just to estimate the number density on Earth, you can use conservation of flux. The incoming flux is just the virialized galactic number density times the speed of the dark matter wind. The flux that's taking these particles away is just dictated by diffusion, is parametrically the gradient, essentially a diffusion coefficient times a gradient of a number density, which turns out to be diffusion coefficient number density on Earth over this big step, L virial, that it first takes before random walking throughout the Earth. And if you equate these two things, you find that the over density on Earth, so the number density on Earth compared to the number density in the galaxy, is much bigger than 1 by 2 factors. One is the fact that the thermal velocity is very small. So velocity at room temperature is very small compared to the velocity of the dark matter wind. And finally, this ratio of length scales, so this big length scale that it punches in with over the small length scale after it cools down is also very big. And both those things can be quite substantial. And so the basic point is that even in the absence of gravity, you get an overdensity. And one way to think about this is that they punch in and then they kind of have to random walk their way out. That implies some enhancement to their residence time. They have to spend some longer amount of time on Earth as they kind of take a while to seep out. And that enhanced residence time implies an enhancement to the number density, even for very light particles that care nothing about the gravitational field. Okay. So in the other alternative limit where they're much heavier than the mass of the proton, this is the case where they'll come in, cool down, and then drift towards the center. They're gravitationally bound. And they're gonna, as I showed you before, want to sink towards the center. But this sinking velocity is v drift and can be very, very small if they're highly collisional. Okay, if they're very collisional, the terminal velocity is small. In that case, just equating flux gives you that the overdensity is enhanced by the small drift velocity over the wind. So over the speed of the dark matter wind. So this can be quite substantial for large masses as well. And it's simply the statement that just the fact that they have to slowly sink through the room implies a large number density, even though those particles will never come back. On average, they'll sink towards the center. The fact that they have to sink through us implies a large overdensity near the surface. Okay, so this is this later population that's more relevant near Earth's surface if you're interested in trying to directly detect it. So you can calculate this using the full profiles of the Earth for the number density profiles of atoms and temperature profiles and compositions, all these things. And I'm showing you the results of the overdensity in the plane spanned by the charge and the mass for positive particles or negatively charged particles. The nature of the interaction matters a little bit because in the strong coupling regime, repulsive versus attractive can change how these interactions look if you're not in the essentially the Born regime of interactions. But you can see for a large range of masses, these overdensities can be quite big near the surface. They can be as big as 10 to the 15, 10 to the 16. They peter off as you go to higher masses and smaller masses, but they can easily be much, much larger than 1. Okay, but where you see these green regions petering off, this is where these particles just aren't able to thermalize. They're not very strongly coupled to the Earth, so there's some steep fall off to these overdensities as you dial down the mass or dial down the couplings or increase the masses substantially. So I just want to make this basic point, though. I don't want you to take those numbers too seriously because they neglected some other important physics, which is this statement that these particles may or may not couple to long-range electromagnetic fields. And this is set by the dark photon's mass. So I described how these interactions could work from the point of view of a kinetically mixed dark photon that's massless before. If that's the case, these particles really do couple on all length scales in most cases to long-range electromagnetic fields. But if the dark photon has a mass, this essentially screens that interaction on longer length scales. So depending on whether or not they do, this can give rise to various effects. For instance, if they couple to the long-range nature of Earth's magnetic field, they can get swept away, or they can get funneled towards the poles, okay? Just like the Van Allen belts for cosmic rays. This happens for a range of couplings shown here. There's also effects that can go in the other way. So there's a large voltage between your feet and the top of the ionosphere of roughly half a megavolt. If you're a positively charged particle, and you're able to thermalize, if you just have a charge greater than 10 to the -7, you'll get trapped under the crust. And this can enhance the local density. It can essentially prevent evaporation of these particles, even for very light particles that are not gravitationally bound. So the point is, depending on the dark photon's mass, the length scale of this interaction, you could imagine degrading these numbers that I just showed you or increasing these numbers. So I don't want to take any of those things too seriously. It's a very complicated problem. There's also the effects of the solar wind. People haven't done a full solution going from I am some fraction of the dark matter and done the full analysis and calculating what the density is on Earth. What I just showed you in the previous plot ignored some of these long-range effects. So instead, the approach will be let's parameterize our ignorance about these things. There are various ways that the number densities can be quite substantial, but I'm not going to buy into a particular model point and instead just label the model not just by 2 numbers, not just the charge and the mass, but 3 numbers, the charge, the mass, and the local density of these particles. And mapping that local density back to the dark matter fraction is a very complicated computation. No one has really done it yet. It's a computation you could imagine doing for particular classes of models, but I'm going to treat this as a free parameter from the point of view of talking about detection. So you could ask, in principle, how could you detect this population of particles? How would I differentiate it from just free ions in the air, which near the surface, produced by natural radioactivity, is at the level of 1,000 per cubic centimeter or so. And the main distinguishing feature is that these particles chi can penetrate a shield. So you can make a good vacuum, you can expel all your free charged ions. These things can't get back into past a conducting surface. But if you have a charge of smaller than roughly 10 to the -1, you can work out that these particles can actually efficiently penetrate shielded material. So you can't create a good vacuum of these particles. And that will be the main distinguishing feature. So just to give you an example of one class of experiments that people have thought about, So in fact, dating back to a paper by Dan Carney and then another one by Peter Graham and Hari Ramani and some others a few years ago, they asked, what would these particles do? The fact that they can diffuse anywhere, they can kind of penetrate any environment, what would they do to an ion trap? And an ion trap is interesting because the walls, although cold, of an ion trap are much warmer than the effective velocity of the trapped ion. So if these Millicharged particles could come in, scatter off the wall, then scatter off the trapped ion, they would effectively act as an anomalous source of heat transport from the walls to the ion, which is observed experimentally. It's usually attributed to be noise. So just from observations of anomalous heating of cold ions, these people have placed bounds on this parameter space. Remember, once again, we need three numbers: the charge, the mass, and an assumption of the ambient number density. So for an ambient number density of 1 per cubic centimeter or 1,000, these different regions correspond to different ion traps that ran at different temperatures. You can bound different parts of the parameter space at extremely small densities. But that's not what I'm going to be telling you about today. What I want to tell you about is how, using much older technology, we can actually cover a very different part and potentially much larger region of parameter space. Okay, so that's what I want to tell you about next. So how can we go after these terrestrial populations using these Cavendish experiments? And I should warn you, so this is based on this upcoming work. I should warn you, this is going to be very, very basic physics, like very basic electromagnetism. I know you guys know this, so this is not meant to insult anybody, but put your mindset into the mindset of the frontier of theoretical physics in the late 1700s, okay? And that will be essentially what I'm taking you through. But it will have strong applications to these classes of models, so that's the motivation. So starting out very basic, you're probably familiar with the idea that Coulomb's law implies that if you charge up a spherical shell and there are no charges on the inside, the electric field is zero. Okay, and this is because you can draw a little, one undergraduate explanation for this is you can draw little solid angle pieces, the area here and the area here scales with the distance squared away. And so if you have a uniform surface charge on the sphere, the ratio of charge over distance squared cancels between one little patch and another patch, and you can do this in a pairwise fashion for all solid angle elements. Okay, so this is the basic argument for why an electric field inside a charged shell vanishes for Coulomb's law, but in fact is more general. You can take a cavity of any shape, charge it up. If there's no charges on this inner cavity, this inner hole here, the electric field is zero. And one simple heuristic way to explain this is that the electric field has zero curl in the static limit. So if this is a good conductor, there's zero electric field in the conducting body. You might be tempted to draw a little Gaussian surface around here and impose that the total charge around that surface is zero. All that tells you is that the total charge is zero. There could, in principle, be positive charges over here and negative charges over here, which cancel. But that would imply that you could draw a non-zero electric field line here, then close the loop, and this loop vanishes. So you would find, in that case, the electric field would have non-zero curl, which it doesn't in the quasi-static limit. So therefore, you're led to conclude that if for a cavity of any shape in the static limit, there are no charges on the inside, the electric field is zero. Okay, this is a very powerful statement. It was appreciated in some sense in the late 1700s. So what I'm going to be talking about is before Coulomb's law was even called Coulomb's law. It predated the notion of electric fields, but people knew about electric forces, had arguments from how it's scaled, actually dating back to some interesting things suggested by Ben Franklin. This was to some degree known physics back then, but it's a very important, a nice thing that the electric field vanishes. That's your theoretical prediction, because you're not limited by systematics. If you want to test this, you don't have to say, my prediction is that the electric field is 1.013 something something in some particular units. It's zero. And so you're kind of independent of a lot of theoretical systematics. So it's a great thing to test. So that's what Henry Cavendish attempted to do in the late 1700s. And he did the following experiment. He took an outer conducting shell and connected it via a wire to an inner conducting globe, and effectively charged up this outer shell to the best of his ability to a high voltage, and asked, is there an electric field generated on the inside that would violate Coulomb's law, that would drive charges to the inner shell? So if Gauss's law of Coulomb's law holds, there should be no charges driven to the inner shell, but he wanted to test this. So he charged it up. He had a way to cut the wire. Specifically, he had a little string leading out that he pulled, broke the wire. This outer shell had a way to open up, which after cutting the shell, he then discharged this outer shell, hooked this thing up to a voltmeter, and didn't see any charge. Okay, so he wasn't able to measure any charge. In fact, he didn't even use one of these voltmeters that you're seeing here. He used something like one of these very old electrometers where you touch charge on one end and two little gold leaves should repel. He didn't see any repelling. And based on that, he was such a good experimentalist. You can see one of his sketches here that he was in the late 1700s, he was able to test the scaling, so the power in Coulomb's law, up to 1 part in 100. So a 1% test of this quadratic scaling. Ultimately, this was limited by systematic noise. There are various things that can accidentally charge up your shell when you're taking it out. There's systematics that we're unable to know for sure what limited him, but some form of systematic, and there are various ones that can come into play, limited the sensitivity of this. So this has been done throughout history. One that happened 150 years later in the 1930s by Plimpton and Lawton is shown here. And here, the basic idea is the same. They have two shells. So here's an inner reference plate and outer shell that they're going to charge up. It's quite large. The radius was 2.5 feet. So this is this is a very big shell. And they're charging it up to 3 kilovolts. But the main distinguishing feature is that they're no longer doing it in the DC limit. They're alternating the voltage at a couple hertz. Okay, and by alternating it, they can get rid of a lot of these systematic sources of noise. In fact, they were only limited by thermal fluctuations of the voltage. So just the comparison of the voltage here and here, for a voltmeter at room temperature, you expect microvolt fluctuations, and that's what they observed. A cute thing, you might ask, if this voltmeter is on the inside, how do they actually observe it? Well, they placed a little glass panel here, but then you might say, well, now this is not conductive. They thought about that, so they put something like salt water or saline solution over the top of it. And this had a shared field of view with a mirror that they could look at from a safe distance with a telescope. So they charged up this whole thing, looked if they could see this wobbling, the voltmeter. They saw it fluctuating at a microvolt level, which is what you would expect for a voltmeter of roughly the size at room temperature. And from this, they were able to impose a bound on Coulomb's law and the scaling of not 1 part in 100 like Cavendish, but 1 part in a billion back in the 1930s. Okay, so these things are often discussed within the context of testing for a non-zero photon mass. This is a particular violation of the standard Coulomb's law because the scalar potential would now have a finite range set by a non-zero photon mass. One way to say this is that Gauss's law would have a new term on the right-hand side here that scales like the photon mass squared times the voltage. So this way of thinking of the modification of the Coulomb or Gauss's law is quite nice. You can think about this new term as an effective charge, not a literal charge, but it's a new source term, something that can source an electric field. So if you charge up a shell, to leading order, the inside is a fixed voltage, phi 0. So you have this effective charge density, which can source a new electric field. Okay. So in fact, thinking about it that way, you can ask how were these people testing the mass of the photon back in the day? They didn't think about it like this, but effectively Cavendish was testing the fact that the photon had to be lighter than 10 to minus 7 eV back in the 1700s. So electromagnetism from his test had to be longer range than something like a meter. In the 1930s, Plimpton and Lawton essentially were able to bound the photon mass at the level of 10 to minus 11 eV in this way by going to Hertz frequencies once again. So their main driver was an alternating current. And there have been various other tests throughout history. In fact, Maxwell himself was an admirer of Cavendish, and roughly 100 years after Cavendish repeated the experiment, but just did it a little bit better, and did roughly an order of magnitude better in terms of the photon mass. There are experiments from the 60s and 70s which did much better, namely because they're going to higher frequencies. So kilohertz and megahertz allows you to cut down on noise, but also, of course, because they're using higher voltages, better detectors, things of that sort. But the main feature that you'll notice is here, this is essentially static, mild frequencies, higher frequencies, the limit's getting better, and this is caused to some degree by a fall off in noise. But regardless, I still want to focus on this 1930s experiment. And the reason for this is because I've kind of been taking you through a bit of a meandering, different story from the main point of what I've been telling you about. I've been telling you about tests of Gauss's law or Coulomb's law. Here, I'm mainly interested in about millicharges to bring it back to the central point. And unlike, these are not approximately like relativistically propagating signals, they're very slowly moving signals. So the rate at which this signal builds up will be slowed down by the rate at which these particles can diffuse throughout your experiment. So for that reason, and I'll explain why more technically, you don't want to oscillate these frequencies or these voltages too quickly. You want to give time for this slowly moving Millicharged background to kind of build up in signal. So the perfect trade-off between good sensitivity, but not too fast of frequencies is roughly a hertz. Okay. So just to recap, I told you about this story about large terrestrial overdensities, how these Millicharged particles can build up on the Earth. And second, these tests of Coulomb's law or Gauss's law or the photon mass, which were done in the late 1700s and also these ones in the 1930s and 70s. But now let me kind of relate them to each other. Okay, so I'm interested in how these experiments can test for a background of Millicharged particles. So let's imagine we have a shell of radius r0, and you have some unknown background of Millicharged particles sitting here with some net neutral background. And you charge up this shell, just like in these experiments. What's going to happen? Well, this Millicharged background is going to do what a plasma does. It's going to discharge that shell. So you're going to bias negatively charged particles, in this case, to have a number density inside the shell greater than the positively charged particles. So this will contribute some charge density rho, which will give rise to an electric field. So essentially the violation of Gauss's law here is a trivial one in the sense that you just have charge densities that are present that you didn't know about. So to figure out the strength of this effect, the simplest limit to take is the weak coupling limit. So imagine you're charging this thing up to voltage phi 0. Let's consider the limit where the electrical binding energy of these particles is much smaller than their temperature. Okay, so they're not going to get stuck in the shell. They're just going to be slightly biased to sit inside it. And just to simplify the calculation, you can invoke Boltzmann statistic. You don't have to do this. But if these things have a Boltzmann statistics in their phase space, the charge density is set by this difference of Boltzmann factors. But the difference between the negative charge and the positive charges. And if you expand this out in the weak coupling limit, you find that the charge density on the inside is set by something that's called the Debye mass, which is just controlled by the charges, the number density, the temperature. The temperature being in the denominator here is important. In fact, this is an enhancement to the effect. The slower moving these particles are, the larger the signal, okay, unlike scattering signals. But you'll note that the size of this charge density is very similar to the photon mass case. So I told you before that the photon mass gave rise to an effective charge density that went like photon mass squared. Here it's Debye mass squared. So there's some weak analogy in the weak coupling limit between photon masses and Debye masses. And I should say I had to invoke Boltzmann statistics here, but I didn't have to do this. In fact, to first order in the coupling, so in the small coupling limit, you can show that for any Millicharged background or any plasma background, whether it's collisional or collisionless or any kind of phase space, this result still holds, but this temperature gets replaced by some average kinetic energy of that phase space. Okay, so this is interesting, but something more interesting happens in the different limit, in the strong coupling limit. So let's take the limit where these charges are sufficiently big, and they don't have to be so big for this to be true, but they're big enough such that the binding energy of these particles to the shell is much bigger than their temperature. Okay, so in this case, these particles will move in, and if they're able to exchange energy, scatter off of stuff, if they move into the shell, they're going to be trapped there. They're not going to evaporate. Okay, so the rate at which you can accumulate these things depends on how fast they're drifting in. So there's essentially a drift velocity dictated by the electric field and reduced by the collision rate, but this is just the terminal velocity of these particles moving in. And you can essentially just count how many particles are coming in. And when you do that, you get a charge density that scales like the answer you had before. So something that scales with the Debye mass squared, but now has a ratio of time scales. So it has this just time of how long you've run the experiment, t, over this thing, which is the radius squared over the diffusion coefficient. This is the time it takes for these particles to diffuse a distance r. Remember, it's like a random walk. So the time to go a distance r scales like r squared, where, just as a reminder, this diffusion coefficient just tells you about how strongly coupled these particles are. It goes as the mean free path times the thermal velocity. So this means it's very similar. This result is similar to what you had before, but it's enhanced by the integration time over a diffusion time, which can be large. But an important question to ask is, what sets this timescale t? I would like this to be as big as possible to enhance the effect. And it's essentially just the collection time, how long you can run the voltage. But of course, remember what I said before, is that the best experiments aren't keeping their voltage fixed, they're oscillating it. So this collection time t is essentially just an oscillation time of the voltage, which for this 1930s experiment was on the scale of seconds. So this implies actually something pretty important. The fact that there's a finite collection time to the system implies something important about how well these particles are able to move past the wall. Okay, so if they're unable to diffuse quickly, there's going to be a strong suppression. So let's just zoom into this region here. And imagine particles getting pulled into the shell, but the voltage of the shell is oscillating. Okay, now it's a very simple calculation in fluid dynamics, just setting up boundary conditions. I'll save you the calculation. It's essentially one line of algebra. But what you find is that the profile, let's call this distance of the barrier x, this profile of the charge density scales like this. This is the exponent of this quantity. So it becomes exponentially small if this barrier size is too big. This x squared over diffusion coefficient, once again, is the time to diffuse throughout this region. So if these particles take too much time to diffuse into your experiment compared to the oscillation time of your voltage, then the signal becomes exponentially suppressed. Okay, so this is kind of obvious, but this tells you the degree to the suppression. And so for this reason, a lower frequency is preferred. So it's this reason that this 1930s experiment, although not the most sensitive, is the most interesting one from this perspective, because they were oscillating at hertz and still had good sensitivity. So this gives a chance for these signals to build up. So you want to avoid this exponential penalty. You can ask, what is their sensitivity just rephrased in terms of charged particles? Effectively, what they're sensitive to is 1,000 electrons worth of charge rushing in and out of their device every second. So of course, electrons couldn't do this. Only millicharged particles can really just pass through their apparatus easily. But you need 1,000 electrons of charge worth of millicharged particles for this to happen. So of course, I should say, this 1,000 electrons worth of charge is the accumulated charge, not just the ambient charge, but the accumulated one that you gather as this voltage is turned on and off. So just looking at this old 1930s experiment, you can actually recast existing limits. Okay, so these are limits from this 1930s experiment, assuming a mass, charge, and an ambient number density. And you find that this experiment is sensitive to ambient number densities as small as 1 per cubic centimeter, or 1,000, that are otherwise untested. So there are certain features of this limit. I don't have time to explain all of them, but let me just explain a couple. So at very high coupling, you'll note that the reach falls off. And this is because this is where these particles become so strongly coupled that it takes them too long to diffuse into your experiment compared to an oscillation time of the voltage, which was a second in this case. At very high masses, you'll also note that the sensitivity falls off. This is because this is where the gravitational force from the Earth just becomes more than the electrical force of the shell of the experiment. So these particles will just get ripped in straight lines down throughout the experiment and tugged away and pulled towards the center of the Earth. But in this parameter space, this experiment is interesting. You can break it up in a different way. So this is just the same result, but now broken up, where now the left panel only assumes 1 per cubic centimeter. The right panel assumes 1,000 per cubic centimeter. And these light gray regions to compare are limits from ion traps. And you'll note that this old 1930s experiment here and here in blue is actually competitive and complementary to these ion traps experiments, which to me is completely impressive. It's kind of crazy that technology separated by 90 years, 80, 90 years can actually be competitive in this way. The main reason for this is that these blue regions, this old 1930s experiment was inadvertently taking advantage of collective effects of millicharged particles as opposed to looking for single scattering. Okay, so that gives rise to some enhancement in the signal. It's just a different kind of signal. Okay, But in the last few minutes, I just wanted to answer a final question. So I told you about all these old things. What would you do now? Okay, so how would you optimize with a dedicated setup? And I'm not really talking about any fancy new technology. Let's assume you time traveled back into 1936 and told them about Millicharged particles. What would they do to build the optimal detector? I will talk about some modern twists to amplify the signal. Essentially, the only modern thing that we'll need is approximately good vacuum. Nothing comparable to the LHC or LIGO of that sort, but maybe a little bit better vacuum than you could build in the 1930s. But essentially, let's take the same noise levels that they had in the 1930s and ask, what can you do as a dedicated experiment, not to test Coulomb's law, but to look for these backgrounds of Millicharged particles. And before I describe the idea, let me describe the problem that we want to overcome, which is this statement about diffusion time versus oscillation time. So there's this tension about slower oscillation times of this voltage being good because they enhance the collection time. But as you go to lower frequencies, you just have a wall of noise that starts increasing from various systematic effects. So how are you overcome this problem of greater collection time but increased noise as you go to smaller frequencies? And the simple fix is just to take this same experiment that I was just showing you. So this is the same Cavendish type experiment where you oscillate this outer shell, okay? And you have some reference shell on the inside. So this is the same standard kind of Cavendish style experiment that I was describing to you before. And it has an oscillating voltage, but now you surround it with a bigger shell whose voltage is kept constant. Okay, so you imagine surrounding it with a big shell at a much higher voltage, just fixed to something constant. And only this interior one is oscillating. So what does that do? Well, this outer shell just gobbles up charges. And it gobbles up charges for as long as you run this experiment. So effectively what this is doing is it's rescaling. You're no longer looking for the ambient density of particles on Earth. You're looking for the ambient density of particles that you've gobbled up for how long you've run this experiment. So instead of the charge density on the inside here, scaling with the oscillation time, it scales with the total integration time of this big trap shell, which can be a day or a month or a year, however long you choose to run this experiment for. So you essentially undo this suppression. So you can go from a second to a year. Okay. The other assumption that I'll be making is that this region in here is an approximately good vacuum. So that will allow these particles to diffuse throughout this experiment more easily. So essentially the diffusion time is just limited by the scattering off the shells, not scattering off all the air molecules inside here. So that's the only essentially like modern assumption that I'm going to assume about this. Okay, so what if you can charge up this outer shell to something like a megavolt or maybe 100 kilovolts? It doesn't matter too much. That essentially just sets this lower boundary. And run this thing on the scale of months. You can ask, what ambient density are you sensitive to now? You're sensitive to incredibly small densities of these particles, 10 to minus 12 per cubic centimeter shown in this dark blue. Okay, so this is an extremely small density. This corresponds to testing particles that make up a very, very small fraction of the dark matter. And this is essentially just the same 1930s experiment, but just surrounded by a high voltage fixed high voltage shell under approximately good vacuum. But these densities are so small that it's not the most interesting application is no longer looking for things produced cosmologically. You could now look for the irreducible density of things produced by cosmic rays. Okay, so I didn't tell you before in too much detail, I just mentioned it briefly, but you can calculate, given the mass or charge of these particles, you can calculate the density of these particles produced, and you can run them throughout the Earth. So you can find out where they effectively cool down, and you can solve some fluid equations, and they kind of diffuse around, take some steps, eventually leave. But the fact that they kind of take a while before leaving implies an enhancement to the number density. So the non-relativistic flux of particles that are produced by cosmic rays and then scatter, the density of those particles is typically bigger than the density of particles that are produced relativistically and just pass throughout your apparatus. So this is something you can calculate using the same formalism that I showed you before. So let me just show you essentially the reach. So if you do this dedicated experiment, something that we think an advanced graduate student could do. This is the reach to these particles, whether or not they make up the dark matter. Okay, so this is just testing for the irreducible density these particles produce from cosmic rays. You'll note that it's doing substantially better than limits from accelerators. There's a bunch of accelerator proposals people think about that can kind of eke out into some new parameter space as well. But to me, it's pretty cool that you could just do a very simple experiment without any fancy technology. Just charge up a shell. In fact, people sometimes do these experiments for college labs in physics. But if you did it in this dedicated way, you could potentially have a substantial new portion of sensitivity, just whether or not these particles exist in nature, which is quite interesting. Okay. So with that, let me conclude. So I told you about terrestrial overdensities of dark matter subcomponents. So particles that make up a small density of dark matter that can have an overdensity on Earth. These densities can also arise from cosmic rays, as I just mentioned. These things are interesting, one, in the sense that cosmologically, it's very trivial to have things that make up a very small density of the dark matter. Okay, it's just very simple cosmologies can give rise to these particles. But an additional motivation is that there's extremely large gaps in coverage. Okay, so these particles could exist at the GeV scale with pretty sizable interaction rates, and we just wouldn't have seen them yet. But just trying to think about alternative ways to look for them can open up new possibilities. These large gaps imply that maybe rethinking older experiments are more interesting than previously thought. So I told you about these Cavendish experiments, which just from the 1930s just recast can be new limits on this parameter space, or are new limits on this parameter space. And furthermore, unsurprisingly, how therefore simple dedicated setups can probe a very large region of unexplored theory space without new technology, just dedicated setups using old technology, but in a special way. So various questions you could ask is, I focused on one set of models here. You could ask, are there other kinds of models where this is relevant? That's kind of a difficult question to answer. It turns out not to be so obvious, but happy to discuss if you guys are curious. But something I think that is probably true is, are there better analogous tests? I wouldn't be so surprised. We just kind of thought of the most obvious modification that you could do these Cavendish tests, but I wouldn't be surprised if there were even better ideas. I think there's a lot of low-hanging fruit. And I'll end there. Thank you.
So for your kinetic mixing story, if you had a CP violating kinetic mixing, then they get a magnetic charge.
Ah, yes, I know you've worked on this, right?
So I'm waiting to hear what you think, or you haven't looked at that yet.
I haven't looked at that yet. I don't know the parameter space as well. I know from your papers and from I think Anson wrote a paper on it as well, that it's relatively unconstrained. Experimentally, if you have magnetically millicharged particles, it's a little bit harder because there's not a standard model analog, as far as I'm aware, that can just be a simple trap. Like for an electrical interaction, you can just have a point source. You just take something that's literally charged under an electric field, and now it's just an attractive well. I would have a harder time thinking about like a standard model analog that could be a trap, for literally magnetically charged particles, or effectively magnetically charged particles. So I'm not sure. I mean, it's funny you mentioned it, because when those papers were coming out, including yours, I thought a little bit about how to make some analogies. The one thing that's in your favor is that it's much simpler to make very big magnetic fields in the lab than electric fields. So you can't excite an electric equivalent of a 10 Tesla field electrically. Like an electric field unit, you can't do that, but magnetically you can. So these trap experiments I would have a hard time thinking about how to trap them, but there would probably be, and I haven't thought about it too much, there would probably be a lot of interesting avenues to try to bend these particles and set up little disturbances and try to detect it. So it would probably be hard to gobble them up for a long time, but I'm sure you could do radical things to them. But I haven't thought about it too much. It's a really good question.
You show that this type of experiment can reach beyond the collider search. Does accelerator search include those Millikan or Formosa experiment?
Yeah, good. So I didn't show any projections here. There, I didn't show any projections. Maybe I should. Yeah, so some of those projections are either slightly worse or competitive with this idea. Yeah. Yeah, but sometimes, but like, yeah. So I mean, there are some experimental projections that are substantially worse than this idea. So it kind of depends. But that's a good question. I haven't looked at all the projections carefully enough, but I know what you're referring to, and I think there's parts of this parameter space that they have comparable sensitivity. Yeah.
But a Cavendish experiment costs a lot less, I would guess.
Yeah. I mean, I think you could literally do this in they teach these experiments in like grad student labs. I found a lab manual from somebody who teaches how to do this in like a Princeton lab. So I think that one advantage that we have here is that you could do this really quickly. You don't have to wait for a beam from the LHC or anything of that sort. I think if we waited 10 years to do this experiment, it might not be interesting anymore because those LHC based experiments, as far as I understand, have a real good possibility of just reaching the sensitivity that they plan on doing. But if someone wants to do this within the next several months or year, I think that's something they can do. That's something that they can do. In fact, I think Peter Graham was talking to Tony Tyson there, and he expressed interest in doing this because he apparently has done some of these Coulomb's tests before, and I guess never published those results, but it's something that's in his wheelhouse.
Cool. Something you can do without DOE functioning.
Yeah, that's right. So a 10, right? Whatever it is, a 14% proposed cut to the Office of Science won't affect these kinds of experiments because these are basically free anyways. Yeah.
We have an experimentalist hiding off in the corner
Oh,
on the
Yeah,
line,
also Matthew.
An expert.
but they're not saying anything.
yeah. I think the only required skill set here is sufficiently good high voltage training. I mean, me personally would not want to deal with this. I'd be scared of high voltages, but I think that's mainly the thing that's required.
Yeah, 120 volts scares me.
Yeah. Exactly.
Any other questions? Let's thank Asher
Okay.
again.
Thank you.
Okay, I'll turn off the recording.